I am excited about this next talk. So please give a big hand for Yusun Zheng.
Okay. Good afternoon. It's great to be here today. My name is Yusun Zheng. Today, I'm going to present about this, real-time network analytics for Telco company. So, let me introduce myself. I'm working for SK Telecom as a senior engineer. SK Telecom is the biggest communication service provider with more than 50% of Korean market share. I have worked programming cloud computing until 2013, and now working in programming related to big data things in a telco company. If you have any question about today's speech or related job, ask via this email freely. Let me introduce today's topic. First, I'll talk about big data in SK Telecom. And second, I'll talk about why SK Telecom chose Spark as its core technology. Third, I'll talk about real-time network analytics in SK Telecom. I'll share two use cases using Spark Streaming and Spark SQL. I'd like to share what is challenge and how can we solve the problems for Spark real world. I hope it will be a helpful reference for architecture using Spark. Finally, I'll talk about SK Telecom ongoing R&D project. Let's start with a bit of big data information of SK Telecom. I will tell SK Telecom as SKT for making it short. SKT is biggest share of carrier market in South Korea. South Korea is one of the countries with high smartphone user rate and high-speed communication. Now, the number of mobile subscription is bigger than the population in South Korea. Since 2013, SKT has been established and operated its own hard clusters. Hard cluster in SKT collect approximately 250 terabytes a day. This system consists of more than 1,400 nodes, and the nodes can be a cluster for any opportunities. Some servers are converted to Hadoop from MPP-based DBMS server after migration. We, SKT, adopted Spark from 2 years ago, applied to building a data warehouse, real-time computing, and data analysis, and etc. We collect variety data and analysis from it because of upgrading network quality and service level. Use case of Spark I share today include two sections. First, I'm going to explain about real-time processing and analysis from network data. Second, I'm going to share knowledge for data integration and creation of Hadoop data warehouse. Also, I'm going to talk about our ongoing R&D project. It's a Hadoop data warehouse appliance with meta query engine and hardware acceleration. Okay, let's start with Hadoop infrastructure of SKT. I have stated before that SKT is the biggest communication service provider in South Korea. SKT receives huge volume of data in every second. For recent several years, data traffic has been enormously increased as LTE, long-term evolution, has spread in South Korea. To manage the network quality and to analyze the service, we have established Hadoop clusters. The name of the entire cluster is Big Bang. In the Big Bang, Small and big planes are born and die according to the business requirements. The incoming data are various motion logs in diverse data type. About 250 terabytes are incoming to the Hadoop cluster from more than 100 data collectors. At this time, through the post-processing, the corrected data are refined and stored according to the data type and its purpose. Each service cluster, here the planet, is used for various analysis and services. Introducing use case for today is focused on network analytics. For 3 years, we managed optimized configuration of large-scale clusters. We SKT also have the operational know-how of managing over 1,400 nodes. We have the experience of various failure and solve the problem. This is what makes us different from other companies. Our experience and knowledge to solve any problems in big data management and processing. This chapter is going to show big data reference architecture of SKT. Depending on the business requirement, data is processed real-time or batch job using Spark. Here one, on the batch layer, data is loaded in Hadoop through Flume and ETL is run by Spark. Enterprise data warehouse based on Hadoop is representative example. Here, two, on the real-time layer, data collected through Kafka is processed by Spark streaming. Real-time analysis could be a typical example. Here, three, on the analytic layer, data is analyzed with multiple Spark analysis libraries. And here, four, all the resources within the Hadoop cluster are managed by Yan. Finally, here, five, on data service layer, a commercial BI tool, legacy system and applications are operated by interworked. In this chapter, I'll talk about why SKT Big Data choose Spark as its core technology. Spark, above all, is developed a variety of applications from core itself and is easily and quickly built up. Powerful point of Spark is this: support for event stream processing and fast data queries in real time, improved programmer productivity, and fast batch processing of large data set, and so on. From benchmark test result at SKT, data processed with Spark is faster than any other technology on our case. Of course, there is an exception. However, at least, performance will go to further continually. Let's get into network analytics, main subject of this session. Real-time analytics is the first subject on network analytics. First, Apollo. Apollo stands for Analytic Platform for Intelligent Operation. This is the name of real-time network analytics platform of SKT. With real-time analysis of access network data, we attempt to improve operation efficiency with your access network. Second, Network EDW is Hadoop-based enterprise data warehouse using Spark to assure end-to-end network quality and problem analysis. The Apollo aims to improve mobile user experience, reduce operation cost, and improve operation efficiency by analyzing radio access network. It collects variety logs and data process in real time and improve operation efficiency by real-time monitoring, analyze based operation, and relate analysis. Apollo collects and analyzes raw data from base stations in real time to optimize the service performance. It handles 6 terabytes a day, covering 100,000 cells. Data from base stations are transferred to Kafka and passed and processed as Spark streaming. An RDD step in both Elasticsearch and HDFS in this time. Elasticsearch is adapted because Apollo is web service. It processes and makes statistical data from each 10-second data burst with Spark streaming. If data exceeds the threshold, it automatically detects as abnormal data in this moment. We are trying to optimize the real-time user and service level. It predicts traffic variation and base station performance and minimize degradation in the base station and user performance. Requirements are as follows. Data processed in 10 seconds, wherever data is big. Response time after processing should be fast. This is data process flow in Apollo. 1. Kafka producer. Data from Flume is sent to Kafka broker via Kafka producer. 2. Spark streaming. Data flows from Spark streaming to Kafka direct stream, and it makes processing and statistics data of 10 seconds from the data after sorting by time. 3. HDFS. Data saved at HDFS and Elasticsearch respectively. Challenges for this are as follows. Due to the speed up for parallel process in accordance with increased data, surprisingly, the partition of Kafka also increased proportionally. The executor should be larger considering the amount of data and processing time too. Sometimes the processing time is over 10 seconds. RDD is stacked into HDFS is a bottleneck. They code, collect, and write from all workers. Akka programming method is adapted for it. Asynchronously writing to RDD to process ends up in 10 seconds. I also use the packet with the data format to make a short. Now I want to return to the data process of Apollo. 4. ES. Data saving at EX makes a chart interworking with web pages. Chart made by 10 seconds and processed by Elasticsearch because Spark SQL cannot follow a requested speed each time. In this case, I'll show you later. In the view of hardware, SSD is adapted as Elasticsearch storage to make it fast. 5. Spark SQL. JDBC interface is needed for BI tools and related analysis from HDFS data. Data response is fast as possible at interface. 6. Spark MLlib. We are applying Spark MLlib to streaming process for the detect outlier. The Apollo web screen is as follows. It is a real-time metric monitoring screen for each base station. This web page shows data querying Elasticsearch to the chart each 10 seconds. Using dashboard, network operator can be detected problems on base stations instantly. This is anomaly mining screen. Target analysis data is searched by Spark SQL. Threshold would set upper and lower bound by sigma value of historical data. Data exceeding threshold will make an alarm. It is detected outlier is only one metric, so it sometimes causes a port alarm. For example, the resource usage metric sends an abnormal alarm. In this case, it is normal status because data trapping metric is increased by a user. So we are trying an outlier detection of the correlation metric using a Spark MLE. In this chapter, I will talk about Hadoop-based data warehouse. Hadoop data warehouse provides a Hadoop architecture-based data warehouse from an enterprise environment, so the user can accommodate the massive amount of increasing data at a low cost. Existing legacy IT infrastructure, it was a high-cost, high-performance data warehouse. Data warehouse infrastructure of SKT is made up of cost-effective IT infrastructure system to the architecture of applying the SQL on Hadoop technology. Let's move on to enterprise data warehouse based on Hadoop as a second use case. It's about network enterprise data warehouse. Data scientists want to get enterprise platform which can collect data from all network equipment through efficiency measurement and analysis. Measurement of network separate each individual systems. The system constructs over 130 legacy DBMS. So it's very hard to analyze in total network view. Network EDW merge data into Hadoop to make analysis of the cause of network failure fast and accurate. For next, I'm going to talk about architecture of network Hadoop EDW. Data collect from various network devices and stack into Hadoop. ODS is saved in the Hadoop on the first step and is changed to data mart after a pure ETL process. The data mart is linked as JDBC through Spark SQL. We developed meta query engine for user and permission control. Meta query engine also can make an integrated query for different type of databases. BI search databases and tables that is permitted via meta query engine. Last chapter, I'll talk about meta query engine more detail. Through the network EDW, user can do end-to-end analysis for quality assurance and port analysis. Moreover, analysis read time reduces a few minutes from a few days. It can save TCO 1/5 less than legacy data warehouse. We, SKT, optimize Spark SQL functions and query to build Hadoop data warehouse with Spark. And also, SSD caching applied for performance enhancement and bulk loading and timely processing of large data. Main requirements are as below. ETL batch process running time. Volume of data produced variously because all network device is corrected and ETL runs too. In defined time, data should be processed efficiently. Process flow of user query will be next. Here, metadata system, here MDS, run the ETL through the UGI. And meta-query engine, here MQE, manages the schema information from metastore. BI tools will connect meta-query engine to load the information accessible databases and tables. Here, HA proxy. Thrift server can be configured in a redundant through the HA proxy. In this chapter, I share some configuration for performance enhancement. Dynamic resource allocation is adapted for process efficiency when ETL and BI interwork. SKT use YAN as cluster measure. When ETL runs through UGI, executor is assigned by each job. It's not easy to set number of proper executor because some jobs need to handle large amount of data. For this, we use YAN dynamic resource allocation of Spark. With it, we can manage executor flexible by workload at ETL and BI interwork. Add this at configuration files and allocate minimum and maximum settings number at executor. If Thrift server need interwork with BI, I put a higher initial number. This chapter focused on setting a path for BI integration. We use the Spotfire BI tool internally. The BI loads a bunch of data from data source through JDBC. To reduce memory usage of Thrift server when the JDBC is in use, I set it as follows. Basically, I set the value of Spark SQL Thrift server incremental collect as false. With the false setting, RDD is uploaded to the Thrift memory at once and transferred to the client. If you change it to true, RDD is uploaded to the memory by the partition size. And the default of Spark driver max result size is 1 GB. The BI tool of the SKT is used in this way. The data is loaded at once, and the filtering and pivoting is done inside. So I changed this value to 10 GB. This chart shows that the query response time is shorter now than with the default configuration settings. Next, the Spark patch issues of this project. We try to improve the Spark SQL performance and implement SQL functions. Our code contributions and reported issues are detailed below. Most of issues contain support function of BI interworking and SQL optimization. On the side of performance enhancement, we tested data format on SQL, Spark SQL. A set of TPCH queries was used for a benchmark test, aiming to find the best file format using Spark SQL. I used scale factor 100 GB for this test and ran the TPCH query 3 times. The response time given is an average value for the 3 queries. I also uploaded the TPCH kit to my GitHub page. You can download and check it. The response time is for each data format is as follows. Parquet format with snappy compression shows better performance than ORS with snappy. And Spark also supports partition discovery and schema merging using Parquet. For ETL, we use a Spark Submit request to Yarn resource manager for acquisition of Pro4 resources. In the case, it took much time because each ETL process should submit an application to Yarn. Then each ETL process generated their own Spark context. From the ETL side, the data is loaded into the 2,500 table every 1 hour. It causes a delay in time for each Spark context generated. If you are using the Spark job server during the ETL, there is no need to generate a Spark context every time. We reuse Spark context, so we could reduce the processing time remarkably. I will show you the actual BI2 screenshot of this page. We collaborated between Spark SQL and BI2, here SparkPire, internally. Data is loaded in bulk by SparkPire and requested after filtering and pivoting. This is another page. For the last, ongoing R&D. It is the current state of R&D in progress. We at SKT are developing Hadoop data warehouse appliance combining advanced query engine with hardware acceleration. We are aimed to next year first quarter. Next chapter, I will describe Meta Query Engine as core software solution and SSD caching as hardware acceleration. I'll talk about Meta Query Engine in more detail. As I mentioned, SKT developed Meta Query Engine. Octopus is the project name of Meta Query Engine. Octopus is a unified SQL query interface for polyglot persistence system. Current, it provides authentication and authorization features similar to regular database systems. We also adapted these functions to network EDW system. Octopus will provide NCSQL interface over heterogeneous databases, including Hadoop systems, RDBMS, and many NoSQL systems. This project is currently hosted on GitHub. For more detail, visit this URL. This chapter shows Octopus architecture. It supports SQL interface and JDBC interface. We use the Apache Meta model for schema and data source management, and using CarSite for query planning and execution framework. The goal is to make users feel like they are using a single database systems, which actually consists of several database systems. If you have any idea about this project, please join us. Additionally, I want to elaborate a bit about the hardware acceleration of the SSD that I explained before.